Welcome to another discussion on logic. This time we're going to tackle sets and Venn diagrams. Venn diagrams are going to be a great way of visually seeing what's happening. So a set is simply just a collection of objects. The members of a set are just the individual objects within it. We write sets by listing all their members out within a pair of these little squiggly brackets. We use three dots. I think it's called an ellipsis, to indicate a continuing pattern if there are too many members to list. So like if you're going to list out, all of the positive integers, you would do 1, 2, 3, 4, 5, comma, dot, dot, dot. So you would know that it just keeps going on and on. And then a Venn diagram is just a diagram that uses circles to represent sets and how those sets interact with each other. Here's a simple example. Use braces to write the contents of each of the following sets. So the set of countries larger in land area than the United States, or the set of natural numbers greater than 5. So the set of countries larger in land area than the United States is only Russia and Canada. So those are two, right, in squiggly brackets. And then the natural numbers greater than 5. Natural numbers is a fancy way of saying integers, right? So it's just 6, comma, 7, comma, 8, comma, dot, dot, dot to let you know that it just keeps going on and on and on out to infinity. Okay, so Venn diagrams are just ways of showing how things interact with each other. So for instance, we saw this in one of our previous videos where we talked about if something is a whale, then it is a mammal because whales are a subset of the mammals, right? So when you have the Venn diagram of a circle inside of a circle, you know it's a subset because the set of whales is a subset of mammals because all whales are mammals. But you can also see that this also does not mean that all mammals are whales because you have all of this stuff out here that are not whales, right? So all mammals are not whales. Okay, how about if we have fish and mammals? Well, those two things don't intersect because a fish and a mammal, those are two different, genus of things. So there's no overlap, there's no intersection between fish and mammals. Okay, how about doctors and women? Well, there's an overlap, right? It's not all women are doctors, so it wouldn't be a subset, and not all doctors are women, so that wouldn't be inside that one. But there is an overlap, right? And this little football shape represents female doctors. This little shape, I always say it's a cookie with a bite taken out of it. Those are male doctors. And then this cookie over here, those are just women who are not doctors, right? So that's how the Venn diagram works, and that's how it tells us what's happening. And there's no, like you don't overlap these more to show that this is a bigger proportion. We just always use this same symbol if there's any overlap, whether it's, one woman in the whole world, or, like 75% of women are doctors. It doesn't matter proportionally what it is. We just keep this shape looking the same as far as the overlap is concerned. Okay, so some relationships that we can get out of Venn diagrams. We've seen that when you have one circle inside the other, it tells you that it's a subset. When we have two circles that aren't touching, that's what we call our disjoint. It's just a fancy word for meaning they don't have anything in common. And then if they are overlapping sets, then we just say they are overlapping sets, which means they have some sort of intersection, right? They have some sort of commonality. Okay, here's another example of disjoint things, right? You're either a Democrat or a Republican. You can't be both. Now, you could obviously have Democratic thoughts, beliefs towards some things and more Republican beliefs towards other things, but as far as registering with a political party, you have to register with one or the other. You can't be both. And then, of course, the other stuff outside those would be all the other political parties, the independents, people who just aren't affiliated with anything, the Green Party and all that kind of stuff. Okay, so you can describe the relationship between the two from the picture, and we know that they're disjoint. You can't be the same thing, right? You can't be both at the same time. So let's draw a Venn diagram showing the relationship among the sets of natural numbers, whole numbers, integers, rational numbers, and real numbers, and then where are irrational numbers found in this diagram. So if you've forgotten the meaning of these sets, you can see the brief review on page 29 of our textbook, or you can Google it, but basically this is what it looks like, right? We've got ways of classifying numbers and they just become smaller and smaller groups. So we start with the real numbers. And the real numbers are basically just everything you can think of on a number line. Decimals, fractions, whole numbers, negatives, square roots, pi, e, everything out there is a real number. And then the imaginary numbers are out here. And the imaginary numbers are the things that have the square root of -1, which are, very rarely used, but that's why they're called imaginary. And then the real numbers are really cut up into two sets. The irrationals, which is this outer ring, and then the rationals. And rationals, by definition, are just any number that can be represented by a fraction. So all decimals are fractions in disguise, right? All whole numbers are fractions because they're just something over 1. The only thing that aren't rationals are the irrationals, and those are the things that can't be listed as a fraction, and those are things like square roots, right? And pi and e and all those weird, strange numbers. And then within the rationals, right, fractions and decimals and stuff like that, we have the integers, which are the whole numbers. Well, integers we can also call whole numbers, which is a subset of the integers that don't include negatives, right? So integers can be -1, 2, 3, 0, and +1, 2, 3. The whole numbers are just 0, 1, 2, 3, and then the natural numbers don't include 0. They're what we call the counting numbers. So that's how those work. They're just subsets of each other. Okay, how about categorical propositions? So categorical propositions must have the structure of a complete sentence. One set appears in the subject, the other appears in the predicate, whatever the heck a predicate is, right? And for example, in the proposition, all whales are mammals, the set whales is the subject set and the set mammals is the predicate set, right? So the subject set is the first part and then the predicate set is the second part when we're talking about a subset of something. So we normally use the letter S to represent the subject and P for the predicate. So we can rewrite all whales are mammals as all S are P, where S is whales and P is mammals. And then we can see all S are P, and then no S are P would be no fish are mammals. Then we have some SRP, right? Some doctors are women. We could also write it the other way and say some women are doctors, right? There's no real reason why one has to be the first one and one has to be the second one. Just like some S are not P, which means some teachers are not men, right? We could also say some men are not teachers. So the whole predicate thing, it doesn't matter which one is first and which one is second. The statement, some dogs can swim, you can kind of rephrase that to some dogs are animals that can swim. So that's how it gives us kind of those two groups. So we have the group of that is just animals that can swim, and then we have the other group that are dogs. I mean, you could have group 1 would be dogs and group 2 would be things that can swim, right? Because you don't have to be specific that's an animal. You could just say things that swim, and that would still be the intersection, right? So here's your Venn diagram where S is dogs and predicate are animals that swim. But again, like I said, you could go either way. The S and P's can be switched. Okay, consider the study summarized in Table 1.1, which is an example of a two-way table. This study was designed to learn whether a pregnant mother's status as a smoker or non-smoker affects whether she delivers a low or normal birth weight baby. The table shows 4 numbers which correspond to the 4 possible combinations of the baby's birth weight status and the mother's smoking status. So here that is, right? They can either be a smoker or a non-smoker, and then the baby could have low birth weight or normal birth weight, and here are the numbers. So, A, we can make a list summarizing the 4 key factors shown in the table. B, we could draw a Venn diagram to represent the data table. And C, based on the Venn diagram, we could briefly summarize the results of the study. So we start off, make a list summarizing the 4 key facts. 18 babies were born with low birth weight to smoking mothers. 132 babies were born with normal birth weight to smoking mothers. 14 babies were born with low birth weight to non-smoking mothers, and 186 babies were born with normal birth weight to non-smoking mothers. Now we can put all those numbers together. So we've got the intersection between smoking mothers and low birth weight. So we can see that these 14 babies were the low birth weight ones that came from non-smoking mothers. These 18 came from the smoking mothers and low birth weight. These 132 were smoking mothers who had normal birth weight. And then these 186 were the normal birth weight from the non-smoking mothers. Now, based on that, who knows, right? They say that the Venn diagram makes it easy to see how smoking affected babies in the study. Really? I look at this and go, I don't see that. I mean, I see it better from these numbers and go, the non-smoking mothers only had 14 versus 186. And I could simply do this as a percentage and say that, 14 is a pretty small percentage out of the total, right? If you add 14 to here, that gives you 200. So 14 out of 200, that's only 7%. Then if we add 18 to here, that becomes 150. 18 out of 150, that's over 10%, right? So a higher percentage. That's the way I would look at it. I honestly don't see how this tells me anything, but maybe you guys can see it better than I can. But they're trying to say that Venn diagrams can help with this. I'm not so convinced. Venn diagrams really just help you kind of, in my opinion, help you see where the numbers land. So if you look at all the different types of blood types, AA negative and so on and so forth, and then put the percentages in there, you can see where blood comes from, right? AB positive comes from a mixture of all three. B positive comes from a mixture between B and O positive. A positive becomes from A and A positive, right? And then if you have A without the O positive, it's just A negative and so on and so forth. So you can see kind of where the blood types come from, and then you can fill everything in with their proper stuff. So that's to me, that's the better application of a Venn diagram, is you can then figure out overlaps and you can subtract from them and then figure out which numbers go where and that kind of stuff. So if anything, I would pay more attention to this type of example than this type of example, because I don't see that as being hugely convincing of the argument. All right, that's Venn diagrams. Hope it helps.